Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the Space Nuts podcast. And we are celebrating episode 180, which is extraordinary because I can't count that high as a general rule. And joining me, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I am well. 180 episodes.
It makes me think you and I should get a life, you know.
Yes, you're probably right. Although, you know, I enjoy this so much. I really get a kick out of it. And I'm so thrilled when we get emails and messages from people to say how much they love it too. So, you know, that's fantastic. And we are dedicating this whole episode to questions from the audience. Most of these are fairly recent questions, and they've certainly got their brains working at 90 to the dozen to try and come up with some thoughts and hopefully us come up with some answers. Well, I'm just going to sit here and look like an idiot. But, we'll get into those shortly. I've got to tell you, Fred, astronomically speaking, yesterday in town we had a massive smoke haze because we had an easterly breeze and that brought in all the smoke from the coastal fires that we've been having these last few weeks in New South Wales. And I thought, gee, when the sun sets, there could be some really good photos to be taken. So I took my camera down to the end of the road because there's a hill behind us and the sun sets behind it this time of year with a grove of trees on top. And I thought, I'm going to get some great snaps. Boy, oh boy, did I. They are amazing. I particularly like the one where the sun was behind a grove of trees, and I took a close-up at 40 times optical zoom, and it looks like the trees are on fire. It is, you know, I showed them to you. Tell me how good they are, Fred.
Your photographs are very good, Andrew. No, they're great. No, they're spectacular. Of course, what you're seeing there is the effect of scattering. As the sun sinks down into a smoke-laden atmosphere, this phenomenon of Rayleigh scattering kicks in. It only works if the particles are small, so you can probably tell by the amount of red light that you were seeing around the sun just how small the particles were. But no, it's fantastic stuff, really good stuff. Yeah,
one of my favourites is one I took from the backyard over the neighbour's yard, and he'll probably want royalties now because one of his plants had a leaf turned up in a sort of a cup shape, and I actually got the sun sitting in it, which looks really nice. So I'm very happy with them. They are on my Facebook page if you want to track me down, and my Instagram page as well. I've put some there, and on Twitter, and on Tumblr, and on Pinterest. I've got photos everywhere. But,
so, dear listeners, you probably get the impression that Andrew is quite proud of these photos.
I really
quite
am.
rightly so. I'm
really
just
happy with them. Yeah, they turned out beautifully.
Yeah.
Anyway, we better get down.
Can I tell you what I've been doing this week, Andrew?
Yeah, well, you better fill us in.
Not photography, but we were very honoured this week to have a visit from Linda and Tom Spilker. And you probably will recognise that name. Linda is the Cassini project scientist. So she came over at the invitation of the Department of Industry, Innovation and Science to do some talks for us. So on Monday, we were at Macquarie University doing a public lecture there, and on Tuesday at Questacon in Canberra doing a public lecture there. And she also gave a colloquium to the Planetary and Earth Sciences Department at Macquarie. So Linda is a fantastic person. She is not only the mastermind behind what I think is one of the best ever robotic planetary exploration missions. But she's a really nice person as well, and was so generous with her time. We had some very, very long and really interesting chats about not just Cassini, but many other aspects of spaceflight as well. Tom, Linda's husband, is a planetary scientist too, and a space engineer, and his passion is for spacecraft which have artificial gravity, and he's currently very deep in the design of a spacecraft which would be, I can't remember actually, it's of the order of a couple of 100 meters in diameter, very much along the lines of the space station in 2001, A Space Odyssey, but it has lunar gravity. So it rotates at just the right rate to give you lunar gravity. And that's to allow all kinds of commissioning to be done for instruments and equipment, not to mention astronauts who will eventually go to the moon. It's brilliant stuff. It was an exciting couple of days.
Well, we have had a couple of questions in recent times asking about the development of artificial gravity. So there it is. It is actually something that's been seriously considered. So,
yes,
yeah, that's exciting news. Let's move to our first question. This one comes from Andrew Hugh Parker. That's 3 people, by the way. So, another 60 Starlink satellites are in orbit, and a bunch of fresh articles smashing SpaceX over how they are a threat to astronomy itself. I'm curious to hear what people are actually saying in the astronomical community. How much do these articles reflect the thoughts of the astronomy community? I would expect that SpaceX have done their research into this. I would also hope that if it indeed posed a threat to astronomy, they wouldn't go ahead with their plans. In saying that, though, they aren't the only company dreaming up plans for a mega constellation. Surely at least one of these companies would have taken astronomy into consideration, especially SpaceX and Blue Origin, both chasing space exploration with astronomy being critical to their mission. Fred, what's going on? Asks Andrew Hugh Parker. Thanks, Andrew.
Yeah, Andrew, that you kind of touched a nerve there, because that's absolutely right. There is a lot on the web. It's come to this has, of course, been brought to the attention of the world by the fact that SpaceX launched 2 batches of 60 satellites, one in May, one in November, and these are relatively bright objects. They're in low Earth orbit, but they are just the precursor for a much larger constellation of satellites. In fact, the Starlink program that SpaceX is undertaking eventually will have, well, the number is 11,943. That's the number quoted in orbit. And that's just one of a number of projects to launch constellations of satellites, which number in the thousands. And these are specifically for internet access, to give the world the same sort of access to the internet that you get from, the center of a European city, for example, or something like that.
Yep.
Really high-speed broadband. It is an issue. There is no question about that. And there has been quite a lot of work done within the professional community to really try and quantify the risk. What's happening, in terms of how will it impact on the imagery that's being carried out by large telescopes. The bottom line is that the telescopes that will be most affected by this are imaging telescopes. That's to say, ones that take images rather than taking spectra. The rainbow diagnostic that we use such a lot in astronomy. Imaging telescopes, but particularly wide field telescopes, those with a broad field of view. And we kind of know about this. When I used to be connected with the United Kingdom Schmidt telescope, which for its first 30 years took survey images of the sky. These were on photographic plates, of course, rather than CCD detectors. But we noticed the number of plates steadily increasing over the history of that telescope with satellite trails on them as the number of satellites actually increased. Now, that, of course, was in an era when you could probably count the number of operational satellites, well, not on the fingers of one hand, but not much more than that. And now we're talking about a completely new era. So wide field imaging telescopes will be most affected. Perhaps the one most critically affected will be the LSST, the Large Synoptic Survey Telescope, which is being built not far from La Serena in northern Chile. That has a wide angle of view, and its job is to rapidly image the sky, so it covers the whole sky every week, just about. I think it's every 6 nights, and that perhaps has, of all the professional telescopes, that's perhaps the one that might be most significantly affected. Of course, the other large area where wide-angle imaging telescopes are used is in the amateur community.
Yes.
Amateur astronomers are doing this all the time, and they
probably
too.
Many of our space nuts community.
That's probably right as well. So there will be an effect there. So yes, advances have been made to these companies. Elon Musk says he is engaging with the astronomical community. He's talked about coating the spacecraft with low reflectivity material to try and minimize the optical reflection. But there is no doubt that he's aware of it. The community itself is there's a whole spectrum of responses, from absolute outrage to we've just got to get on with it. One of the issues with SpaceX, I think I'm right in saying that some of their spacecraft are in pretty low orbits. I think 550 kilometers is the lowest orbit that they will use, and are expected to decay fairly rapidly. So it's a more fluid population of satellites. Nevertheless, it's a lot, and especially if we've got many other companies doing the same sort of thing, we might see a doubling of that number. We might be talking about 20,000 spacecraft. So very interesting stuff, a very interesting time for astronomy. I don't believe it forecasts the end of optical astronomy, as some people have said. I think there's much more to it than that. But we will survive. But yes, it's an interesting issue. And the big, the best outcome, or perhaps the way to deal with this, and I think this is really what's happening, is dialogue between these operators and the International Astronomical Union, particularly, and telescope concerns like the Large Synoptic Survey Telescope.
So it won't affect radio telescopes, because I would imagine, because there's so many of these and they're all using radio signals, they'd have to block out some of the spectrum.
Well, so the radio spectrum's already divided up into, into bands that are available for communications and bands that aren't. And my recollection, I did look at this when back in May, when that first tranche of satellites was launched by Starlink, and I think we're pretty clear of the critical wave bands that are used in radio astronomy, but that bandwidth is always under pressure. The communications industry always wants to try and extend the range of frequencies that they can use, and of course the radio astronomy fraternity basically pushes back on that, because these are frequencies that if you cloud them out by satellites, and when you think about the square kilometre array in Western Australia, it's in the most radio quiet part of the world. If you've got satellites going overhead that are broadcasting on frequencies that are used by the telescope, then you've got bad news. But my recollection from what I looked at earlier is that that's not the case.
Okay, there you are, Andrew. Hopefully Fred has told you what's going on. Thanks for your question. Let's move on. I love this one, Fred. This is a beautiful email from Francesca in Cincinnati. Hi, guys. Go the Bengals. Andrew, dismal season so far. Yeah, last I looked, Francesca, they were 0-9. That is not a good season. Anyway, she goes on to say, I'm a junior astrophysics student at the University of Cincinnati, currently working with a professor of mine on cosmic microwave background radiation and finding gravitational waves using BICEP and Keck in the South Pole. I've been listening to you guys for almost a year. I even played your show through a speaker at an observing event at Cincinnati Observatory, where I volunteer. We have the oldest continually operated telescope telescope in the Northern Hemisphere. Your show never fails to make me smile. That's lovely. I was chuffed today listening to episode 175, I think, where Andrew said that in his opinion a young girl won the telescope picture contest on Facebook. That was me. I was freaking out that I was, albeit indirectly, mentioned in my favourite show. I have a quick question. I was hoping Fred could clarify gravitational lensing for me. I understand that in some Hubble images there is a foreground galaxy which distorts the image behind it, almost acting like a magnifying glass, but I just can't get my head around how it works. Thank you so much. You guys are seriously the best. Lots of love from the US, Francesca. P.S. Fred, give Mandu a kiss for me. He is easily the cutest cat I follow on Twitter. That's lovely. Love that.
Will, next time I see him. I'm in Melbourne. He's in Sydney. We're several hundred miles apart, so I can't do it just now. But that's all right. He will get the kiss in due course.
Excellent. Good to know. Excellent.
So, which brings us to gravitational lensing, because it's objects of high mass that cause gravitational lensing, and Mandu is definitely an object of high mass. he's a very fulsome cat, very large. So you've explained it as you've asked the question. It all comes from the predictions of Einstein's general theory of relativity, published in 1915, that says that gravity is in fact not a force, as Newton said, but a distortion of space, which we perceive as a force. So even the Earth distorts the space around it, and that's why things stick to the Earth's surface, because the force at at your feet, the shape. Sorry, let me put it the better way. The shape of space at your feet is slightly different from the shape of space at your head, and that's what keeps you pulling downwards. And that is true no matter what kind of gravitating mass you've got. It actually is. It was the sun's effect in doing this to the space around it that allowed relativity to be demonstrated back in 1919, when I think it was the 22nd of May, an eclipse was observed by Eddington and others, which showed that when the sun is eclipsed, and so you're not seeing the light of the sun, what you can see is stars around the edge of the sun, and those stars had basically been distorted in their position. They moved in towards the sun, apparently, because that. I beg your pardon. They moved away from the sun. Get it right, Fred. They look as though they moved away from the sun because of the gravitational pull of the sun, and it's because of this distortion of space around it. Now, if you now think of a galaxy or a cluster of galaxies, which is more the usual case with the Hubble images that Francesca's talking about, there's a huge amount of mass there, and so that distorts space really significantly, and that's what gives the origin to these gravitational lenses. Why do we call them gravitational lenses? Because it was probably around 1920, I need to check this, a man called Oliver Lodge, who was a physicist in the UK who didn't really believe in relativity, but he did work through the equations, and he showed that the gravitational lensing effect, if you think of the distorted space around a cluster of galaxies, the effect is the same as you could get with a glass lens, but it's a very unusual shaped glass lens. It's one with a cusp in the middle, and actually the best commonplace analogue of that is the bottom of a wine glass. The bottom of a wine glass has exactly the same shape as this cusp lens that represents the kind of distortion that gravitational lensing produces. That's why it's called lensing, because it acts like a lens, and Oliver Lodge pointed that out. So next time you're looking through the bottom of a wine glass, which I do quite often, and by that I mean
I'm not usually well focused when I'm looking through.
No, I'm sure you're not. Well, that's right. You can do anything when you've got that. By the bottom, I mean the bit that stands on the table. The shape of that, as I said, mimics gravitational lensing. If you look through it, look at a light behind it, and you'll see that characteristic sort of circular image of the kind that you get with those Hubble telescope images from distant galaxies. What you don't see with a wine glass so much, but which is definitely the case, is that the light intensity in the background image is magnified. So there's a cluster of galaxies in the foreground, something very distant in the background that you might not see normally. But the gravitational lensing effect of the cluster is not only to distort the image, but also to amplify the amount of light that you see, sometimes by 30 or 40 times. Wow. So you see something that would be otherwise invisible.
Amazing. There you go, Francesca. Look at the bottom of a wine glass, or just drink a lot of wine and you won't care. But thank you for the question. Thank you for the lovely note. We really appreciate it. You're listening to Space Nuts, episode 180. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by Tech Radar. This is the one I use. I've been using it for a couple of years, and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons, and there was just something about their business model that I particularly liked, and a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, we have a question from one of our patrons. And, of course, if you would like to become a patron, you can do that by visiting the Patreon website, patreon.com/spacenuts. For a mere $3 a month or anything above that you would like to contribute, you keep supporting our program and keeping it rolling along, which we greatly appreciate, and we thank all our patrons for doing that for us. It's voluntary, you don't have to, but it is greatly appreciated. Now, this particular patron is Paul Glaser. Nothing to do with Starsky and Hutch, I imagine. He says, here's a question related to the recent announcements concerning the high-speed ejection of S5HVS1. How is overall momentum conserved in this situation? If we bookkeep mass and velocity for the stars and the black hole, how does the high-speed star get enough momentum to achieve escape velocity from the vicinity of SGA? A gravity assist from a planet like Jupiter for a space probe works, but because Jupiter gives a bit of an orbital momentum to the probe, which doesn't seem to be the case here due to reference frames and such. Paul has got a very deep mind. That was a pretty heavy duty question.
Oh, that's right. Yeah, and it's a good question too. SGA is we usually call it Sagittarius A star. That's the radio source that is essentially associated with the supermassive black hole at the center of our galaxy. Yes, this was a story that we covered a little while ago that involves this high velocity star, usually called S5HVS1, a very interesting object. I can't remember its velocity. It was something, 1,700 kilometers per second. It was by far the fastest star ever seen traversing through the galaxy. And so the idea is that has had a sort of episode near the galactic center that has caused it to be ejected like this. But the bit that Paul's message doesn't cover, he compares that with a gravity assist from a planet like Jupiter, and of course that happens all the time. By the way, the Cassini spacecraft, Andrew, I'd forgotten this, but Linda reminded me when we were talking earlier in the week, it had 4 gravity assists, 2 from Venus, 1 from Earth, and 1 from Jupiter on its way to Saturn during the 1990s and early 2000s. Great stuff. And what happens there is exactly as Paul says. The spacecraft approaches the planet and steals a bit of the momentum of the planet to boost the spacecraft to a higher velocity. The missing ingredient in that, though, and certainly the ingredient that's present in the case of S5HVS1, is that originally this star was part of a binary system. So it was already... there are 3 bodies involved in this issue, not 2, as there are with a gravity assist. The binary star system means that high velocity star would originally have had a companion. They too would have shared angular momentum, but once the flyby of the black hole at the center of our galaxy had occurred, the result of that is a total disruption of the binary system by the gravitational field of the black hole, and it's to do with the fact that it's very rapidly changing as you go in towards the black hole, and that essentially acts as a very large spring, tears away the companion and boosts the high velocity star out at the velocity that we observe of order 1,700 kilometers per second. We don't know what happened to the companion, but there's a really good chance that it gave up its angular momentum to the black hole, that it actually was sucked into the black hole. I'm not familiar enough with the physics of that encounter to know how near it took place. I'm sure that given measurements of the speed and direction of the ejected star, you can actually get some handle on just what happened near the galactic center. But I haven't actually read the paper in that much detail. But that's the bottom line, that there are 2 objects. It's a binary star that has given up one of its companions and booted the other one out.
Very good. There you are, Paul. Hopefully that answered your question. Let's toddle off to, where's this fella from? Doesn't say. David is his name, that's all I know. He says, "Hi, I'm an avid listener of Space Nuts, and this question seeks your response to a speculation." We love speculation, because you can have so much fun with it. I've been watching a video about the Tunguska event. The video leaves the cause of the event open, with a meteor and volcanic gases, or a combination of the two, being the most likely cause. How feasible is it that the area was hit by a meteor that was rich in methane and other organics, which created a vapour cloud as it entered the atmosphere, and that then ignited and exploded, creating the conflicting evidence shown in the video, particularly the absence of large pieces of meteorite material? Regards, David. Tunguska seems to be one of those events that is subject to a lot of speculation and, in some cases, doubt. But I wasn't aware that there were alternative theories, to be honest.
Yeah, there have been a number of things that have been proposed. In fact, some scientists have proposed that it's actually due to volcanism on Earth. That was the thing that actually caused the demise of the dinosaurs, the climate change that led to that. Now, I haven't had time, unfortunately, to watch the video. I will have a look at it, though, because David gives us a link to that. But the last paper I read about this was pretty clear that it was the effect of the meteor, or the asteroid as it was, it's 15 kilometers across, the effect of that on the underlying geological structures and the fact that the asteroid hit in a shallow sea at the time, so there's water involved as well. The chemistry seems to be fairly clear cut that what you've got is essentially a blanket of debris that has reduced the temperature on the Earth very, very rapidly, and caused this breakdown of the food chain and essentially wiped out the dinosaurs. I mean, you're absolutely right, Andrew, that from this distance of 66 million years, it's not really easy. It's not easy at all to pick out exactly what happened. And that's why I'll be really interested to have a look at the video. But the last analysis I read seemed to think that, seemed to present that all the I's have been dotted and the T's crossed. And the reason for that is the new data that we've got from the Myrtle drilling rig that actually drilled into the Chicxulub crater. It sampled something called the peak ring, which is a ring that's formed within a crater like that when an impact occurs. There is all the kind of shocked material that you would find from an impact of such colossal energy, emission. The shocked quartz and things of that sort is all there in the rock samples underneath the region. I think it's remarkable that I think it was in the 80s or 90s that it was the source of that meteorite was identified as the Chicxulub region in the Gulf of Mexico. And of course, the smoking gun that tells you that an impact was involved is that at that Cretaceous tertiary boundary where the dinosaurs disappear in the geological record, there's a layer of iridium. And that was what alerted Walter and Luis Alvarez to the fact that there was probably an extraterrestrial event that was essentially the cause of the demise of the dinosaurs. Now, what David's suggesting, methane-rich and organic-rich asteroids, that's all possible. But I think the idea of an explosion, the explosion really, the amount of energy. As it hit the atmosphere, there would certainly be an explosion there. But the main effect of the impact was actually once the asteroid had hit the ground, and all this stuff is raised into the atmosphere. I will watch the video. I'll have a look because David's question is interesting, and his suggestion is certainly not without merit. But I'd be really interested to see what the video says. So apologies that I haven't had time to do that, David, but we'll get to it eventually.
Okay, very good. Thank you, David, for the question, and hopefully we gave you a bit of information to go on there. I had to laugh the other day, Fred. I was watching a TV show where a satellite crashed back through the atmosphere, and all the people on the ground heard the bang and looked up and saw the satellite. I suspect that wouldn't happen in real life. They wouldn't hear the explosion of its entering the atmosphere at the exact moment it happened. We've talked about this before, so they shouldn't have been able to react to it.
If I remember rightly, for the Chelyabinsk event back in 2013, I think it was about 90 seconds it took for the shockwave to come down from 30 kilometres. So, yeah.
Well, this was an episode of The Walking Dead, so anyway.
You do watch some rubbish, don't you, Andrew?
I do. I'm watching War of the Worlds at the moment.
Time to do that. That's what I don't get. I don't have.
I do, Fred? I watch
down in front of a telly.
I actually watch shows in parts. I don't actually have time to sit down and watch an entire program these days. So I'll watch 20 minutes, and then a couple of days later, I'll just pick it up where I left it off and maybe catch another 10 or 15. It might take me a week to watch a half-hour program sometimes.
Okay, that's the trick, is it? You just got to make sure it's always the same program.
Yes, exactly. But I'm watching War of the Worlds at the present time. I thought I had purchased the new one that had been released by Amazon, which is set in the era when the book was.
Okay.
But I actually got the wrong one. It's a 2019 edition from France, and I got really agitated because I thought, you idiot, how did you do that? But you know what? It's really good. I'm really enjoying it. Okay, you're listening to Space Nuts. Andrew Dunkley with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, if you would like to get some Space Nuts merchandise, you can do that by visiting the Space Nuts shop. It's on our website, BITESZ, bytes.com/Space Nuts. There you will find copies of various publications, including Fred's latest called Cosmic Chronicles, and we've got T-shirts. And the designer of our logo, my good brother Stephen, has been asked to do a new commissioned version of the Space Nuts logo, because apparently if you want to get it embroidered, having more than 4 colours gets rather cumbersome and complicated and expensive. So we've redesigned the logo in 4 colours only, so that we can do an embroidered version of the logo on polo shirts, for example, or tennis shirts, if you want to call them that. So pop along to the bytes.com/Space Nuts shop and have a look around. I would also like to recognise our YouTube followers who are growing in number. We're up to 660 YouTube followers now, Fred, so we want to get to the magic number 1,000. I don't know what that means, but Hugh says 1,000's good because... And that's as much as I know, but it's got something to do with advertising. I don't know. But he's hoping we can get to 1,000. We're well on our way. Now, Fred, we've got another David. This is David from Montreal in Canada, who sends us greetings. I've been a big fan of your show as well as Space Time with Stuart Gary for more than a year now. I always forget to write down questions. So do we. All the questions you've heard today have been completely made up. Anyway, he says he's got one for us. While it's fresh in his mind, he's sent it to us. We all know that black holes evaporate from Hawking radiation and that they evaporate slower as they get bigger. I'm not quite sure if this makes any sense, but theoretically, is it possible that an equilibrium between the black hole's mass lost through Hawking radiation and its intake of photons from the surrounding stars is enough to prevent it from ever losing mass until the stars die out, assuming that no matter is falling inside the black hole? Bonus question, do we have any kind of predictions of what effect it would have if dark matter was falling inside a black hole? Thank you, David Fortin. Okay, Fred. Black holes seem to be the order of the day. People love finding out more about them.
Well, don't we all? That's right. They're such extraordinary things. And we do understand a lot about them, but there are some things that we don't. And David's questions are really interesting. So the key thing about a black hole, and I think David's question, I don't have it in front of me, but I think he mentioned this, that the smaller black holes evaporate more quickly. So the bigger the black hole, the slower it evaporates. And you're talking about timescales that are frankly ridiculous. They're not, they're even ridiculous compared with the age of the universe, which is quite a long time, 30.8 billion years. If you have a black hole of 1 solar mass, the mass of the sun, and that's actually smaller than most of the black holes that we know, but so most of the bigger ones would evaporate much more slowly than this. 1 solar mass black hole takes 10 to the 64 years to evaporate. So 10 to the power 64, you've got rid of your 1 solar mass black hole.
You need a very wide calculator to do that.
Yeah, you do.
Get that number very wide.
Yeah, and I didn't do the calculation. I've just read it in a book called Cosmic Chronicles. Actually.
It's a good book, I'm told. Yeah.
You're right. Yeah,
I haven't got my copy yet. I'm going to.
We should fix that. Anyway, so that's very slow, and it's a really interesting question about how much the mass increases by absorption of photons, and that's something that I wouldn't mind betting is similarly slow. It's not something you can rule out. I'll take the opportunity next time I'm talking to black hole specialists, as I do from time to time, because I know quite a few. I'll ask that question about the increase in mass due to photon absorption. It's a really interesting question. The second part of the question, which has now gone completely out of my head.
Do we have any kind of predictions of what effect dark matter falling into a black hole would have?
Probably, but once again, the thing about dark matter is we don't know what it is. We don't know what kind of subatomic particle it is. It's definitely something like that. you and I have spoken before about the idea of supersymmetry, which has kind of high mass shadow particles for every one of the normal particles, and people talk about neutralinos and axions as being potential candidates for dark matter, but none of the predictions of supersymmetry have yet been verified. And in fact, I think the particle physics community is quickly losing interest in supersymmetry because it didn't seem to be offering any help in trying to understand some of the problems that we find in particle physics, and the problems that we astronomers find in trying to account for this missing 5/6 of the universe, which is the mass of the universe, which is dark matter. So I think it is certainly possible, but I don't think there's any real understanding just because we don't know what these particles are.
So we're living in a universe 5/6 of which we can't, we've defined it, but we can't see it. We don't know what it is.
Well, it's actually worse than that, because if you look at the total mass energy budget of the universe, 95% is stuff we don't know about. And that's because of dark energy. So dark energy falls into that mass energy budget. And of course, mass and energy are related by E = mc squared. That's the link between them. So we know of 5% of the total contents of the universe is stuff we know, and 90% of that is hydrogen, or 99% of that is hydrogen. The normal things that we think of in everyday life are a very tiny proportion of what the universe is really made of.
Okay.
A bit embarrassing, really, isn't it?
Yeah, a little bit, but it keeps you in a job. Thank you, David, for your question. Little side note, today is the day we're recording. 21st of November it is at the moment. You mentioned E = mc squared. Albert Einstein's paper, Does the Inertia of a Body Depend Upon Its Energy Content, was published on the 21st of November 1905, and that paper reveals the relationship between energy and mass and leads to the mass-energy equivalence formula, E = mc squared. So you mentioned it on its anniversary.
Isn't that brilliant?
Yeah.
And that was actually, so he published 5 absolutely revolutionary papers that year, and I think that was the last of them. There were 2 on the special theory of relativity, one that talked about time dilation and things like that, and then he got on to the mass energy equivalence. It's brilliant. So happy anniversary, E = mc squared.
Indeed, yes. What's that mean? It's coming up on its...
114th.
Yes, there you are. I'm glad you did the math. Now, to our final question today from Nick Shack. It's a short, sweet question. In regard to the Mars quakes that have been detected, I thought the core was dead. If there is no dynamo effect, what is causing the quakes? Question. Tidal forces from its moons, perhaps? Thank you, Nick, for your question. I think Nick's been on before with a question or two, so he's always got thought-provoking questions. Do we know what's causing the quakes?
Well, yes, Nick's absolutely right that we think the core of Mars is, well, it might not be cold, but it's kind of much less active than the Earth's core is. And that's actually the reason why the InSight spacecraft is sitting on the surface at the moment. And you and I have spoken recently about the fact that its temperature sensor is having trouble penetrating the ground to sort of see what the heat flow is like from the interior of Mars. So far, I don't think that has advanced any further. But the InSight lander also has that super sensitive seismometer on board to record Mars quakes, and it has done something like 23, I think. I think there's been over 100 events, of which 23 are thought to be genuine Mars quakes. They're much less dynamic than earthquakes are. So, it's not, you wouldn't feel a shaking like you do on Earth. These are much more gentle in terms of the amount of shaking that there is. But the principal causes that would be expected to show up in this, and probably by analysis of the trace of those Mars quakes, you could tell, the principal causes would be, number one, shrinkage of the crust of Mars, because Mars is a cooling body, and as it cools, it contracts. Its crust probably contracts at a different rate from the mantle underneath, and so shrinkage actually causes faulting and things of that sort. That's one possibility, and the other, of course, is impacts by meteorites and small asteroids, because they too would make the surface start to ring in a way that could be picked up by the seismometer. That would probably be the bigger effect, asteroid impacts. So I await with interest a full analysis of the Mars quakes that have been recorded already, just to see what the source of them is thought to be.
Yeah, but we've talked about that shrinking effect before. In fact, I witnessed it the other day, the other morning, Sunday, when I opened the garage door. It had been exposed to the sun, and as soon as it got up into the roof of the garage where it was cooling, you could hear it crackling because the metal was shrinking as it cooled. So I guess that's an example of what could be happening to Mars. It's shrinking due to that cooling effect, and the crackles are Mars quakes.
Yeah, they're garage door quakes, but
garage door quakes.
Yeah, but that's the same effect. Yeah, it's absolutely right. And our fridge at home creaks all the time because of temperature fluctuations in it. It makes the strangest noises, and of course. The thermal shock of when you drop ice cubes into a drink, it often cracks, and that's the same sort of thing. It says its shape changes because of the difference in temperature.
I seem to remember there was a Japanese company that actually harvested ice from Antarctica or somewhere because it was so cold and such a concentration of molecules that when you dropped it into a drink, it would make the most amazing crackling noises. I don't know if they're still in business, but it was a thing for a while.
They would be called Antarctic ice cube quakes then.
Possibly so, yeah. No, it's fascinating. And thank you, Nick, for your question. Really appreciate it. And I think that will wrap us up for another episode, Fred.
It sounds like it. Another decadal episode with episode 180. It's great stuff.
Yes, and we've managed to knock off 1% of the backhaul of questions.
That's all right. Yeah. It's like the mass of the universe.
I think if we can get 95% of them into that part of the universe we don't understand, that'll just leave a handful to do. So that won't happen, of course. But thank you to everyone who contributed to the program. Thank you to everyone who constantly keeps in touch with us and sends us questions. We're working our way through them, but the more we do, the more that turn up. It's sort of like a black hole. But we'll get there one day. Thank you for celebrating episode 180 with us today, wherever you are. And thank you, Fred, as always. It's a great pleasure and great fun.
Yeah, it is indeed. It's always good fun. And thank you for your patience and entertainment in the last 180 episodes, Andrew.
Yeah, one day I might actually get good at this.
Well, we'd certainly need to, don't we, really?
Yeah, yes, indeed. But if we keep aspiring to being adequate, I think we'll be right.
You're right. Yeah. Better than being rubbish as we are now.
Indeed. Thank you, Fred. See you next time.
See you later.
Fred Watson, astronomer at large, and from me, Andrew Dunkley. Thanks again. We'll catch you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.